Okay. Okay, so maybe let's start. So the second talk of this afternoon, before the small break, is Zaher Hani from University of Michigan, who will talk about the mathematical theory of wave turbulence, one of these recent important development related to kinetic theory. Please, Zaher.
Right. Thank you, Clément and Jacob, for the invitation to this very nice workshop. I'll start by apologizing for anyone who has heard this talk before. So indeed, this is a talk on the mathematical theory of wave turbulence, and the central component of this theory of wave turbulence is a wave kinetic theory, which brings us exactly to the topic of this this conference. So let me start with a little bit of an introduction. So this theory of wave turbulence, or wave kinetic theory, it emerged early in the past century, in the 1920s, and it emerged as a way to extend some notions of classical statistical mechanics of particle systems to wave systems. So as everybody in this room knows, statistical mechanics governs macroscopic quantities like temperature and pressure, whereas microscopic quantities like particle trajectories are governed by the laws of dynamics. So these could be classical or could be non-classical, like quantum, for example. And the most important feature of statistical laws, or one of the most important features of statistical laws, is that they are time irreversible. So you think of the second law of thermodynamics, whereas the laws of dynamics are reversible in time, thinking of Newton's laws or Hamilton's laws, Hamilton's equations. So, of course, as we all know, there's this passage from the reversible to the irreversible, which comes as a result of averaging and limiting operations that we do in order to derive the laws of statistical mechanics. But this is what really creates the arrow of time. It also creates this apparent paradox that you are starting from reversible first principles and you're getting something that is irreversible, that could be adequately explained by giving a rigorous derivation of the laws of statistics from those of dynamics. And this is Hilbert's sixth problem in essence, if you think about it. Okay, so this is exactly puts us to the topic of our talk. We will be interested in this Hilbert's sixth problem in the context of nonlinear waves. But before I move on to nonlinear waves, let me give a very quick introduction or very quick recap of the classical example, which is Boltzmann's kinetic theory. And Eric's talk in the morning was a very good introduction to that as well. So Boltzmann's theory tells us that suppose you start with a system of n particles and dilute particles, and each of those particles has a radius r, and we suppose those particles are undergoing elastic collisions. Again, we assume that the initial states of the particles are random and independent, so that each particle has an initial density, say f naught of xv. So this tells you the probability of finding this particle at position x and moving at velocity v. And what Boltzmann's theory tells us that we can give an effective dynamics for the one particle density function. So this is what I call over here fn1 of txv, which is again tells you the probability of finding a particle at position x moving at velocity v at time t. And the central point of Boltzmann's theory is that this is well approximated by the solution of this celebrated PDE, this Boltzmann equation, which you've already all seen before. So there's a transport on the left-hand side, and on the right-hand side, there's a collision kernel that I don't write because I won't be needing it. So Hilbert's sixth problem is the justification of this approximation of the particle dynamics with this kinetic dynamics over here. This was a big challenge, and it was the biggest breakthrough came by Lanford in 1975, and this was culminated, this was extended, and details were filled and culminated in this work of Gallagher, Saint-Raymond, and Texier on the subject as far as I know. So what does Lanford's theorem tell us? Tells us that if we take the limit as the number of particles goes to infinity and the radius of those particles goes to 0, but again, this is not an arbitrary limit. This is something also Eric mentioned in his talk. There's a scaling law that you need to impose. This scaling law tells you that n goes to infinity and r goes to 0, such that this quantity, which is called the collision rate, n times r to the d minus 1, stays order of 1. And in this scaling law, which is called the Boltzmann-Grad scaling law, you have the following two main points. The first one is propagation of chaos, which tells you that in the limit, not before the limit, but exactly in the limit, the states of the particles retain their initial independence. I stated vaguely here. And the second and most important point is that Boltzmann's equation over here appears as indeed as an effective equation for the one particle marginal of the distribution of those n particles, which is this thing over here. Okay, so, and this approximation, one should point out, this approximation holds in the limit only for times that are order of gamma inverse. So these are times that are order of 1. Actually, they are small multiples of that. So this kinetic framework has been extended to much more general particle systems, and the philosophy or the paradigm has been highly informative, and indeed was extended to a lot of other particle systems and gave a lot of other kinetic equations other than Boltzmann's equation. So, so what we'll be dealing with is we'll try to see what the wave theory analog of this particle theory would be. So naturally, a parallel theory of statistical mechanics for waves followed soon after Boltzmann's theory. So this is the first instance, as far as we know, is Peirce's work in 1921. This was followed by the work of Hasselmann for ocean waves in 1962. And then this was fairly invigorated by Zakharov and his school, who made a big link between this kinetic theory and turbulence theory that I will mention very, very briefly in a few slides. So to describe what this kinetic theory of waves looks like, so the microscopic dynamics here, or the first principle, if you like, here, is given by a nonlinear dispersive PDE. So instead of having a particle system that is governed by Newton's equation, we have a nonlinear dispersive PDE that tells us our microscopic dynamics. The large number of particles is replaced by a large number of waves, and those waves are represented by the Fourier modes of the solution of this PDE. So those Fourier modes are in a box of size L, and this L will go to infinity. So that this divergence of L to infinity is the analog of the divergence of the number of particles going to infinity in the Boltzmann theory. And these waves, again, pushing this analogy, these waves undergo collisions with each other, and those collisions are dictated exactly by the nonlinear interactions of the dispersive system that you start with. So for us today, we'll be taking this highly important dispersive system, the nonlinear Schrodinger equation, which is given as follows: T plus Laplacian of V is equal to alpha V squared V. This alpha over here is a parameter in order to characterize the strength of the nonlinearity. We will pose this equation on as we mentioned, on a box of size L. So this is, and we'll take periodic boundary conditions. So this, we denote this by TD sub L. So this is a periodic box of size L in dimensions greater than or equal to 3. A lot of the results also hold for dimension greater than or equal to 2, but they need some qualification, so I just removed that from this talk. Okay, so of course, NLS carries importance in its own right, but it also has a special role and special place in the class of nonlinear dispersive equation, because it has the universal property, which tells you that virtually any Hamiltonian dispersive system will give you NLS in an appropriate scaling limit. So if you cannot do things for NLS, you probably cannot do it for any other dispersive system. Okay, so again, this is again another slide preaching to the choir. Why do we need to study waves statistically? It's exactly the same as in the particle case. We need this statistical theory for waves because of the shortcomings of the deterministic theory. So these are some some PDE perspective from the point of view of developments in the field of nonlinear dispersive equations. So in terms of our understanding of the long-time behavior of nonlinear dispersive equations, when we study those equations on compact domains like TD, or if we study them even on Euclidean space, but we assume that the energy of the solutions is infinite, our understanding of the long-time behavior is very, very poor. And actually, a deterministic understanding is practically impossible. And this is because we have a big zoo of possible long-time behaviors in those settings. So we have periodic behaviors, we have quasi-periodic, soliton-like, a lot of chaotic-like behaviors. So we see a lot of possible behaviors rather than one or a finitely many, if you like. So as a result for that, we cannot just, if you give me initial data, it's practically impossible for me to tell you what is the long-time behavior of this initial data from a deterministic point of view. But even if we study those equations on RD and for finite energy solutions, this is a setting where we believe, or we have a sort of this, we have this belief that we have a good understanding of the long-time behavior, but actually we only have a good understanding of the asymptotic behavior of solutions. For example, if you think of this equation over here, and you pose it on RD, this is the cubic NLS on RD, and for example, on R3, we know that the solutions, even large solutions, we understand their asymptotic behavior. We know that they scatter as t goes to infinity. They approach a linear solution as t goes to infinity. However, while we understand this asymptotic behavior, what is fascinating is that we have a really very poor understanding of the intermediate time behavior. We do not understand what the solution does before it approaches this asymptotic state. And this is again a regime where the kinetic theory gives us a very good insight onto what happens. So as such, one is naturally led to this kinetic theory, and as a result, this statistical approach to questions of long-time behavior, and exactly puts us in the setting of taking or thinking probabilistically about solutions, and as a result, we need to put some, to start with some certain distribution, some random distribution of the initial data while we're studying those problems in the next few slides. So, so as I said, what we will be doing is that we will be starting with, we will keep the equation deterministic, but we will randomize the initial data for this equation. So again, in the analogy of the particle case, we start with the random distribution of initial data. This corresponds to taking random and independent Fourier modes for the initial data of the nonlinear Schrodinger equation. So this is U initial. We denoted that the initial data of the nonlinear Schrodinger equation. We expand it in Fourier modes. Remember, we are working on a box of size L. So the Fourier modes are indexed by K, which is in a lattice of mesh L inverse. And this lattice, when we take L to infinity, will diverge to a continuum. And what we will be doing is that we will be taking the following random distribution for the Fourier modes, which is typically taken in the physics literature. So the amplitudes, we leave it as deterministics. This is given as square root of an initial. An initial is a non-negative Schwartz function RD. This will become the initial data for your kinetic equation. So, you can take it to be Schwartz function. This is an overkill. You just needed to have a finite amount of regularity and decay, but let's not focus on that today. So the amplitude is given by square root of an initial, and then we randomize this amplitude by multiplying by those IID random variables. They are IID normalized random variables, which I denote by eta sub k. For example, you can take them to be Gaussian. Okay, but you don't have to take them to discuss. We will call such data well prepared because this makes the different Fourier modes independent. And more importantly, if I look at the variance of the initial Fourier mode, which is the expected value of u hat of k squared, then this is given exactly by this function n initial of k. And as a spoiler alert, this will be the initial data for your kinetic equation in a few slides. And the goal of this wave kinetic theory is to understand the distribution of the Fourier modes at later times in the limit when L is large and alpha is small. So this smallness of alpha is again replaces the limit R goes to 0 in Boltzmann's kinetic theory, again pushing the analogy here. So, and of course, a particular quantity of interest is the variance of the Fourier modes at later times. So we start with a random distribution of the initial data, and then we propagate by the deterministic equation at a later time t. So we're interested in quantities related to the distribution of u hat of tk at later times. In particular, the variance is an important quantity we'd like to understand. So what does the theory, what does the physical theory predict or state? So this is, I stated here as a kinetic conjecture. What it states is that in the limit as L goes to infinity and alpha goes to 0, so this is the weak nonlinearity limit, which is sometimes called, which is the reason why sometimes this theory is called weak turbulence theory. We have the following three conjectures. So the first one is propagation of chaos. We are starting with Fourier modes that are initially independent. If you turn on the nonlinear dynamics, of course, those Fourier modes will not remain independent. They will interact with each other. They will collide with each other. But magically enough, after you take this kinetic limit, L goes to infinity and alpha goes to 0, you retain this initial independence in a precise way that we will talk about later. And the second point of this conjecture is the kinetic theory. So there's a kinetic equation that dictates the effective dynamics of the variance of the Fourier modes. And this is given by the, this is called the wave kinetic theory. I will write it for you on the next slide. And this wave kinetic equation starts exhibiting itself at a certain time scale that we call the kinetic time scale. This kinetic time scale is exactly 1 over alpha squared. Okay, so alpha, remember, was the strength of the nonlinearity. The kinetic time is 1 over alpha squared. So more precisely, what we predict is that the expected value of the variance of the squared of the Fourier modes, or the variance of the Fourier modes, is approximated by the solution of the wave kinetic equation that I will write for you on the next slide, rescaled appropriately to the kinetic time, plus an error, little o of 1, that goes to 0 as L goes to infinity and alpha goes to 0. We call this property, I will call it later, approx. Okay, so this is really the kinetic approximation that we will be interested in proving. Okay, so here N of tc is the solution of the wave kinetic equation with initial data and initial that we mentioned before, the same N initial that appeared in the previous slide. And U of t solves NLS with the well-prepared data U initial. Okay. And finally, the third point is of this kinetic theory is that we can even try to understand more about the distribution of the Fourier modes at later time than just their second moment or their variance. We can get an understanding of the limiting behavior of the density of U hat of tk, and this density can be described using this same wave kinetic equation. Okay. So this is the kinetic conjecture. What remains for me to tell you is this kinetic equation, to write down this kinetic equation that is doing all this nice work. So this is the wave kinetic equation. I write it here in the homogeneous setting. So this was introduced in the physics literature. It's given in the homogeneous setting is given by dTn is equal to a collision kernel, which is cubic here. And the initial data is an initial. So this cubic collision kernel is given over here. So you have an integral over xc1, xc2, and xc3 in Rd. And such that xc1 minus xc2 plus xc3 is equal to xc. Xc is your variable on the left-hand side. And not only you're integrating over this hyperplane, if you like, but you're also restricting to this variety where xc1 squared minus xc2 squared plus xc3 squared minus xc squared is equal to 0. This is very similar to what you also see in the Boltzmann's equation. You can write the collision kernel to be integrated exactly on this measure as well. And then, so here's the difference. Then this is multiplied by this integrand, which is given over here. Okay. So this is understood as a wave analog of Boltzmann's equation. And again, we have a kinetic approximation that features a passage from a time reversible system, which is the NLS equation, to a time irreversible wave kinetic equation over here. This is indeed time irreversible. You have an entropy for this equation and the H theorem. And I should mention that there is an inhomogeneous version where this N, so here N of C becomes N of, becomes space dependent as well, N of T X C, and in this case, instead of dtn, you would have dtn plus C dot gradient X of N on the left-hand side, and the right-hand side remains the same. I won't be discussing this inhomogeneous version today. We'll restrict to the simpler setting of the homogeneous equation. Okay. So let's talk about some history of this theory in the physics literature. So as we mentioned before, this first emerged in the 1920s. And then soon after, it was generalized systematically to many nonlinear wave systems. And it's used in a very informative way for many nonlinear wave systems. Most notably, there was the work of Hasselmann in the 60s in the context of water waves. There's also, in the context of anharmonic crystals, this is sometimes called the Fonon-Boltzmann equation. It is very much used in plasma theory and in nonlinear optics, and there are many people that have contributed to this theory. And it is, as I said, it is highly informative in applications, particularly in oceanography and ocean forecasting, in optics, crystal thermodynamics, and plasma theory, and many other ways. Probably in the physics literature, the most notable thing about it is that it gives you a formal framework of turbulence for nonlinear waves. And this is why the theory has come to be known as wave turbulence theory. Although I won't be touching on this aspect of this theory in today's talk. But this is all I will say about it. So formally, this wave kinetic equation gives us conclusions similar to those made in hydrodynamic turbulence. In particular, it comes out of this wave kinetic equation some power law spectra, some power law cascade spectra, which are basically just special stationary solutions of this wave kinetic equation. They are called Kolmogorov-Zakharov spectra because they resemble Kolmogorov spectra, and they were discovered by Zakharov in the 60s. So you can see the textbook treatment of Nazarenko if you want more information about that. But what's interesting is that you have those power law, those Kolmogorov spectra and hydrodynamic turbulence appear as stationary solutions of this kinetic equation in this setting, which is a pretty cool thing that's going on here. But this exceedingly cool thing, I would say, is still not mathematically well-founded at this point, despite some very nice works that are taking good steps in that direction, like works of Escobedo and Velasquez, Sofer and Tran. And there's some rigor in those works. You can find some rigorous analysis of the equations. But again, our understanding of the long-time behavior of this kinetic equation is very much lacking. So this is something that should be a very active area of research. Okay, particularly understanding the long-time behavior of this equation and the role that those power law spectra play in this long-time behavior. This is something that's very much poorly understood at this point. Okay, so in the mathematical literature, the history of wave turbulence theory took it's somewhat of took a distorted route, if you like. So as you can see, this kinetic equation has fundamental mathematical implications on the long-time behavior of solutions of the dispersive equation. It's telling us a lot of information. It's telling us information about the variance of the Fourier modes at later time and even the distribution of the Fourier modes of the later time. This is a very rich set of information. The initial focus of the mathematical research related to wave turbulence was a little bit indirect, or sort of inspired by wave turbulence, but not quite hitting the nail on its head, if you like. So the initial interest was to construct solutions for the NLS equation that exhibit some form of energy cascade. So this energy cascade was measured by the growth of Sobolev norms of the solution. So this is a reminder for you of the Sobolev norms. So here I write it on the unit torus TD. But the key point is that when you look at those Sobolev norms, you are penalizing high frequencies much more than you are penalizing low frequencies. So if the energy of the solution goes from low to high frequencies, this will be accompanied by a growth of those Sobolev norms. So this was an indirect way to test the predictions of wave turbulence theory, because energy cascade is one of the predictions of wave turbulence theory from those cascade spectra that I discussed on the previous slide briefly. So this was a question that was posed by Bourgain, and he worked on it on several of his papers. But the most influential work in this direction is the work of Colliander, Kiel, Staffelani, Takuoka, and Tao, who proved that there exist solutions on the unit torus TD that exhibit the arbitrarily large but finite growth of Sobolev norms. So they exhibited solutions that whose Sobolev norm starts small and then at a later time becomes bigger than a certain pre-assigned quantity. Okay, so but those solutions are very special, and they're very hard to construct. It's very, very hard to construct, and they are far from generic solutions. Whether this behavior is generic, which is something that is also implied in a way by the kinetic theory, or whether there exists solutions that exhibit infinite cascade or infinite growth of Sobolev norms, these are outstanding open problems on TD, despite several partial results in this direction. Okay, so and again, of course, if we have a very good rigorous understanding and complete rigorous understanding of this kinetic approximation between the solutions of NLS and the solution of the kinetic equation, then this would give us deep insights, if not a full solution of those questions. So the reason why I said that the approach to kinetic, to the wave kinetic theory or wave turbulence theory from the math community has been indirect, in the sense that even after, so the central question was only addressed much later, only in the past few years. And the central question is, of course, to give a rigorous justification of the kinetic approximation. Okay, so as I already mentioned, why this is something that would be fruitful from a mathematical point of view, but it's also fruitful from a physical point of view, because it allows us to understand the exact regimes and limitations of this wave turbulence theory, which is something that is also needed quite a bit of clarification from the physics point of view. So, but before I go into this endeavor with you, I still owe you one piece of information that I purposefully neglected to mention when I discussed this wave kinetic theory and the wave kinetic conjecture a few slides ago. So remember, in the Boltzmann theory, there was this famous Boltzmann-Grad limit, and in this limit, the Boltzmann equation is derived. So there are similar things that should appear, those what we call our scaling laws in this wave kinetic theory. So basically, a scaling law is what dictates the relative rates of the limits L goes to infinity and alpha goes to 0. Taking those two limits, and most likely you cannot take them arbitrarily to their limits. There must be a scaling law between the two of them, something like the Boltzmann-Grad scaling law. So of course, a priori, you start by considering all the possible scaling laws, and all possible scaling laws, you can write them as in the form alpha equals L to the minus gamma, where gamma is between 0 and infinity, including 0 and infinity. What does gamma equals 0 mean? Gamma equals 0 to mean, you can understand it as taking the limit L goes to infinity first, and then follow that by the limit alpha goes to 0, and vice versa for the limit gamma equals infinity. Well, I won't go too much into the explanation here, but it's not, doesn't take too much time and effort to see that not all the scaling laws would give you a kinetic theory. So not all scaling laws are admissible by the kinetic theory, and there's a range of admissibility, which is, this is the range of gamma. By the range of admissibility, or the scaling laws that are admissible, is exactly the question: what are the values of gamma that are admissible that I can take so that I would get a kinetic theory in the limit, or the kinetic equation that I told you about in the limit? So the admissible scaling laws or the admissible ranges of gamma turns out to depend on the shape of the domain. In our case, since the domain is a box, this means the aspect ratios of the box, okay? So if you don't put any assumption of on the aspect ratio of the box, if you want a general theory that works for any box, then you are restricted to the scaling laws gamma between 0 and 1. So alpha goes like L to the minus gamma, and gamma is between 0 and 1. So in particular, this is the case this is the range for the square box, okay? If you want to impose genericity conditions or differentiating conditions on the aspect ratio of the box, this range can be increased a little bit so that it becomes between 0 and d over 2. Okay, those are both come from number theoretic considerations that I don't think I have time to get into during the talk, but I'll be happy to discuss them afterwards. So the interest in one scaling law over the other seems to depend on the physical context in this setting, but the obvious thing is that you have a range of scaling laws rather than just one. Okay, so let us get to discuss the mathematical results on this derivation of the wave kinetic equation or justifying this kinetic approximation. So there are several works that attempted similar and close by problems, which were an inspiration to the developments that came afterwards. Most notably, there's the work of Erdős, Sonnenhofer, and Yau in the case of the linear Schrödinger equation with the random potential. And then there's another very inspiring work to us, at least, was the work of Lucanen and Spohn that studied the problem of time correlations of an equilibrium Gibbs measure. Other set of works are works that studied a stochastic setting of this problem. So instead of randomizing the initial data, you can add a time-dependent random force to the equation and try to derive a kinetic theory there. There are some partial results, again here, there are not full results. There are partial results by Fau, Dimov-Kuxin, Miyoki, and Vladots, who studied those stochastically forced equations. Okay, but in the deterministic setting that I described, the first attempt at the full problem was in a joint work that we did quite a few years ago, even though it only appeared in 2019 with Tristan Buckmaster, Pierre Germain, and Jalal Shatta. So in that setting, we put ourselves in the setting of the generic irrational toroid, was a technical assumption, and in dimensions d greater than or equal to 3. And in that setting, we justified the approximation between the variance of the Fourier modes of NLS and the solution of the wave kinetic equation. But the big drawback of that work is that while it was the first result of its kind, it only extended to times that are much smaller than the kinetic time scale. Okay, so this approximation only justified it for times that are much smaller than the kinetic time scale. So this approximation interval, we improved it considerably in a later work with Yu Deng, and independently there was work of Charles Collot and Pierre Germain around the same time. So in those works, so this was our very first work, my very first work with Yu Deng in 2019 again. So we improved this approximation interval considerably, so much so that we were able to reach times that are L to the minus epsilon times the kinetic time scale. So where epsilon can be taken to be as arbitrarily small as we like. Okay, so this is still much smaller than the kinetic time scale, but it is sort of smaller by L to the minus epsilon rather than a bigger power factor. Okay, and of course we were only able to do that for some particular scale. We were only able to do that in those work for some particular scaling laws. For example, in our work with the Yu Deng, we did it for the scaling law gamma equals to 1 and gamma equals to 1/2. I remind you here that this gamma equals to 1. By this I mean that alpha is L to the minus gamma. That's what the scaling law is. Okay, so alpha is going to 0 at the rate L to the minus gamma. Okay, so we did it for those two scaling laws. Collot and Germain did it for the scaling law gamma equal 1. And there were later works by Collot and Germain and Mpatsoglu, Collot and Germain, who treated an inhomogeneous equation recently. But all those works, the problem with all of them is that they never reach the kinetic timescale T kinetics. They are always much shorter than the kinetic timescale, and so as such, they do not provide a full justification of the equation, because a full justification of the wave kinetic equation should reach times that are of the form delta times the kinetic timescale, where delta is independent of the two parameters that are they're asymptoting either to infinity or zero. So delta should be independent of L and alpha. Okay, so that's what a full justification of the equation would be, and this is the subject of our main theorem for today. This is again a joint work with Yu Deng from University of Southern California. So we are able to give a full justification of the wave turbulence theory, including the rigorous justification of the wave kinetic equation for some range of scaling laws at this point. So here's the main theorem. So we consider again NLS on a periodic box of size L in dimension d greater than or equal to 3. We take the initial data for the wave kinetic equation to be non-negative, which, as of course, we need to do that. And we take it to be Schwartz, but this is something we don't need to do. We only need a finite amount of regularity and decay. So some weighted Sobolev norm is more than enough for this result, but we didn't care to write it in that way. And as before, we take the initial data for NLS to be well prepared. I remind you what we mean by that. What we mean by that is that the Fourier modes are given by square root of n initial at k, and then we multiply by those IID random variables eta sub k of omega. The only assumption we need on eta sub k is that its law is rotationally symmetric and has exponential waves. For example, you can take this eta sub k to be Gaussian. Maybe you can take them to be independent Gaussians. Okay, the last thing that we need to clarify are the scaling laws for which our result applies. So again, the scaling laws is alpha is like L to the minus gamma, and gamma has to be in this range. So it's sort of close to 1, including 1. But we can also deal with the case, say something like up to 1 minus 1 over 20d. And we recall that the kinetic time scale is 1 over alpha squared. I should point out here, there's a technical assumption when gamma is equal to 1. In the case gamma equal to 1, we assume certain genericity conditions on the aspect ratios of the torus. We assume that the aspect ratios are irrational. And when the case gamma equals to 1, we assume that the torus is irrational, if you like. Then we have the following. There exists a delta, which is fixed, smaller than 1, and an absolute constant nu, such that if L is large enough, we can approximate the variance of the solution of NLS by the solution of the wave kinetic equation up to an error that is order L to the minus 2. So this is exactly what we want in our approximation. This is exactly what the equation that I called approx before. And the key point here is that this approximation holds for times that are from between 0 and times up to delta times the kinetic time scale. Okay, and of course, n is the solution of the wave kinetic equation with initial data and initial. Okay, so this was in our very first work, which I think it was in April of last year. In a later work that we put out in September or October of last year, we continued proving the rest of the assumption or the rest of the kinetic conjecture in terms of propagation of chaos. And we have the following statement. Suppose you take K1 up to Kr to be distinct wave numbers, then we have propagation of chaos. What this means is that the random variables u hat of Tkj, so this is the solution, the Fourier modes, Kj Fourier modes at later time. Again, the key point here is that those things, they are initially dependent at time t equals to 0, but when you turn on the nonlinear interaction, they of course stop being independent. They interact vigorously with each other, but somehow magically, when you take this kinetic limit, you retain this independence. So I find those statements will be really fascinating. I mean, they are facts of nature, but they are really fascinating facts of nature. And the second point is that we can even describe the law U hat of tk, not just its variance. So the variance of U hat of tk is given by the wave kinetic equation, but we know much more statistical properties of U hat of tk than just its variance. So we can describe the density of the density function of U hat of tk. So U hat of tk is a complex number, so its density function lives on R2, and it satisfies the following linear PDE over here. Those two parameters, sigma k and gamma k, are parameters that are completely determined by the solution n of tk of the wave kinetic equation. Okay, and then another fascinating thing to me, another fascinating fact of nature to me, is that this propagation of Gaussianity, that if you assume initially you have Gaussian distribution of your initial data, in other words, if this eta sub k over here, you take it to be IID Gaussians, of course, as you turn the nonlinear interaction on, they stop being Gaussian, but somehow magically in the limit, in the kinetic limit, they become Gaussian again. And what kind of Gaussians? These are they are Gaussians, except that their variance is given by the solution of the wave kinetic equation. Okay, so after we proved those results, we were pleasantly surprised that this PDE that is satisfied by the density function was actually written in 2004 and 2005 in two separate works in the physics literature. So this was confirming some results, formal results in the physics literature. So some remarks on the results. So of course, this provides a full mathematical foundation of wave turbulence theory. And by answering all the three fundamental questions, which are propagation of chaos, derivation of the wave kinetic equation, and the evolution of the limiting density. I would like still to make another remark about the scaling laws. Okay, so this remark, I've already done it. The genericity condition, or the need to assume that your box is irrational, is only needed for the scaling law gamma equals to 1. And in that case, because the kinetic time scale is 1 over alpha squared, which in this case, when you take the gamma equals 1, it becomes L squared. This is a merely technical assumption for number theoretic reasons. But you don't need this assumption for gamma less than 1. For gamma less than 1, you can deal with any torus, whether it's rational or irrational, or any box, and all aspect ratios of the box, whether they are rationally dependent or not. And so for such, if you don't want to assume genericity conditions on the aspect ratios, as I already mentioned, the range of scaling laws is gamma between 0 and 1, and we are in the process of treating all of them uniformly at this point. Okay, so but still, when we wrote this result over here, we were particularly interested in the scaling law alpha equals L inverse, because it is carries a particular mathematical importance based on our interests, at least. So why is this important? Because as we said, so in this case, the kinetic time scale is L squared. And this means that this is the unique scaling law for which gives us results that are order of 1 times on the unit torus. So remember, we are working on NLS on a box of size L, but I can rescale everything to a box of size 1. And if I rescale everything as such to a box of size 1, then this V satisfies the usual sort of non-dimensional, if you like, NLS equation, so V squared V, okay? And because I was dealing with timescales L squared, because of this parabolic scaling in time, when I rescale back to the unit torus, I will have results that are happening at times that are order of 1. So in particular, this would allow us to transfer energy cascade dynamics from the wave kinetic equation to the NLS on the unit torus. Of course, we cannot do that very effectively because in the end, this is still a small data result. This delta is still smaller than 1. If one is able to extend this to large delta, then you would be very much effectively able to transfer results about energy cascade from the kinetic equation back to NLS, and possibly solves a lot of open problems there. And the other reason why this is interesting is comes from the fact that if you do this rescaling again, I shouldn't spend too much time on this, but if you do this rescaling again, you obtain the dynamics of Littlewood Paley projection of the Gibbs measure in 3D, which links our theorem to a very important open problem, which is the invariance of the Gibbs measure for the 3D cubic NLS. This is the only remaining unsolved Gibbs measure open problem for NLS after recent works of Deng, Mahmoud, and Yu. Okay, so what's common between our problem and this problem of invariance of 3D cubic NLS is that both problems are what is called probabilistically critical. And I will explain what this means in a few minutes. And in fact, this theorem that I just stated for you is the very first probabilistically critical result, including in the probability. This is even including the parabolic setting. Okay, before I move on to talking about the proof, I should mention that there was also work of Zaher Hani and Tran that appeared last year as well. So in this work, they consider a high dimensional d greater than or equal to 14 discrete KdV type equation. And again, the problem of deriving the associated wave kinetic equation under a certain scaling law. So their main result is in the presence of a stochastic noise in the equation. So they don't start with random initial data, but for this main result, but rather they have a stochastic noise in the equation that effectively keeps randomizing the phases of the Fourier modes at all times. And in this setting, they give a derivation of the wave kinetic equation at the kinetic time scale. But I should point that the noise is crucial here as it provides an additional randomizing mechanism to the equation, a time-dependent randomizing mechanism to the equation, which is absent in our setting. They do have a conditional result in the absence of the noise for random initial data without noise. So it is a conditional result. So what this means is that they assume certain a priori estimates on the solution. And if they assume that those estimates hold, then they obtain the same result as in this case. They verify that such a priori estimates hold for some restricted initial densities. Those initial densities converge to the equilibrium in the kinetic limit. So they converge to stationary solutions of the wave kinetic equation. Okay, so let's see how much time. I probably have around 10 minutes or so.
Yeah, yes.
Right?
You have about 13, 14 minutes.
Okay, excellent. So I'll give a quick high-level overview of the proof. So the basic point of the proof is that we do a power series expansion of the solution of the analysis equation. So these are the Picard iterates. We write U is U0 plus U1 plus UN plus a remainder. At some point we stop. And each of those iterates, they are multilinear Gaussian expressions that are represented by ternary trees with n branching nodes. These are called Feynman diagrams. So let me draw, of course, the U0 is represented by a vertex, okay, a trivial tree. U1 is represented by a ternary tree, which has one branching node. So this is a branching node and 3 leaves. Those trees will be decorated. We say that they are decorated by the wave number. So this is K, this is K1, K2, and K3. And there are rules for this decoration. So whenever you have a branching node like this, you must have K is equal to K1 minus K2 plus K3. Okay. And for example, for U2, you would have a tree that has 2 branching nodes. For example, something like this. Okay. And in general, you would have a tree that has many branching nodes. So the number of branching nodes is what we call the scale of the tree. Okay. So this means that what we're doing effectively, we are expanding the solution of the analysis equation as a sum of decorated trees as such, where the Fourier transform of UN is being the sum of decorated ternary trees of scale n. So if you're looking at the nth iterate of NLS, you are the nth iterate of NLS is can be written as a sum of all decorated ternary trees of scale n, which means that it has n branching nodes. So if I look at the variance, on the other hand, if I look at the expected, if you had to tk squared, then this over here is just u hat of tk times u hat of tk bar. So this I expanded in trees, this I expanded in trees. Okay, so I have some sort of a multiplication of trees. So when I take the expectation, I would have 2 trees, and I take the expectation of those 2 trees and use the independence of the Fourier modes. So what I end up with this variance is the sum over paired trees. One tree coming from this copy of U and another tree is coming from this copy of U. So this is an example of it. So we call those couples. This is the tree coming from U. This is the tree coming from U hat, for example. And the key point is that those are paired. Those trees are paired. And by this, we mean that the leaves of those trees are paired to each other. And I denote this pairing structure by colors in this picture. So this red leaf is paired with this red leaf. This blue leaf is paired with this blue leaf. This green leaf is paired with this green leaf, etc. Okay, so the moral of the story is that now we have expressed the variance as a sum over couples of trees. Just as we express the solution as a sum over trees, we express the variance as a sum over couples of trees. So we have 2 enemies to overcome here. The first enemy, which is common to such proofs, I would say, is that there are factorial number of such trees. And this is a major obstruction to a power series expansion. Just think of, you have a very trivial power series, an t to the n. If this an grows factorially, then you are doomed. The second enemy, which is again very important in our setting, is this notion of probabilistic criticality. And what this means is that with high probability or with overwhelming probability, the n plus first iterates, okay, of the NLS is only better than the nth iterate by a factor of delta rather than by a power of L. Okay, this is what we call probabilistic criticality. So so probabilistic criticality, this is what dictates the longest time scale for which this power series expansion is valid, if you like. So in our very first work in 2019 with Yu Deng, as I mentioned before, we reached timescales that are order of L to the minus epsilon times the kinetic timescale. It turns out that this is the full subcritical regime for this problem. And in that setting, we had that the n plus first iterate was better than the nth iterate by a factor of L to the minus epsilon. And if you accumulate this gain from the n plus first iterate to the nth iterate, we get that the nth iterate is order of L to the minus epsilon n. Okay, and as such, we only need, if I want this to be less than L to the minus nu, I only need to do an expansion, a finite expansion, up to some order capital N, which is order of epsilon inverse, in order to prove my approximation. So, and this was possible. It was highly non-trivial because this N is still a large number. So it needed some subtle combinatorial structure of the trees, but it is much simpler than our setting here, which is the critical setting. So in this critical setting, the best that we can say about the nth iterate, and we can write down examples for that, is that the best we can say about the nth iterate is that it's better than the n minus 1 iterate by a factor of delta, which means that the best estimate we can hope for the nth iterate is order of delta to the n. And if I want this delta to the n to be less than L to the minus nu, I will need to take n to be larger than a log L. Basically, the minimum is log L over log delta inverse. In particular, I will need to take this order of expansion to diverge with L. And this creates all sorts of new difficulties. And particularly, the main difficulty it creates is this factorial divergence that we talked about. So recall that, as I told you before, the expected value of un squared was written as a sum over couples, but it was a sum over factorial number of couples, where n is the order of the expansion, which was also the number of branching nodes in the trees, right? So, and we just said that there are couples of scale n. So there are some of those couples have size delta to the n. Okay, this is what we concluded in the previous slide. Okay, but if all of them have size delta to the n, then we are doomed. Because then we would have delta to the n times 2n factorial, and there's absolutely no way we can control that. Okay, so for this we need a strategy. And the strategy is as follows. So the strategy is a classification of couples, or those finite classification of those finite diagrams into two groups. First, we need to find out the groups, the couples that saturate or almost saturate the worst case scenario estimate. This is the worst case scenario estimate. This is delta to the n. We need to find out what are the couples that saturate or almost saturate this estimate. And you really hope, because otherwise you're doomed, you really hope that there's only exponentially many of such couples and not factorially many of such couples. So in other words, those that saturate the estimates are relatively few. They're exponential rather than factorial. The second thing that you need to prove is that all the remaining couples, the remaining factorially many couples that are left, they satisfy much better estimate than the worst case scenario. And because you need a gain, so in other words, you need them to feature a gain as a power of L, which is sufficient enough to kill this factorial divergence over here. Okay, we'll talk a little bit more about that. So in other words, since this is really the heart of the strategy, so let me spend a little bit more time on this slide. So in other words, this strategy requires us to do two things. First, as we said, identify the couples with saturated or almost saturated bounds. And one would hope that these are exactly that your first hope, or this was our first hope when we started working on this, that these are exactly the couples that converge to the iterates of the wave kinetic equation. What is crucial here, so this hope turns out to be destroyed very quickly. These are not the only couples, but what is crucial, and this is something that we cannot compromise on, is that there's only exponentially many of such couples. You cannot have factorially many of such couples. And the second very important part is the rigidity theorem that tells you that once you adequately remove those couples that are saturating the bounds, then you are left with couples that feature a major gain, and this gain is large enough to offset the factorial divergence. Okay, so let me talk about those two different points in the following two slides. So I'll talk first about identifying the couples with saturated bounds. So there's bad news and good news. The bad news is that the couples that saturate the estimates are not just those that converge to the iterates of the wave kinetic equation. It's not only the ones that you want them to be large. The bad news is that there are three families of couples that have almost saturated estimate. Of course, the first family is what you're expecting. So the first family is what we call regular couples. These are the leading diagrams, and these can be matched order by order to the iterates of the wave kinetic equation, up to some error terms. The second family, which is the unexpected bad news, is that which we call irregular chains. And these also lead to almost saturated estimates. Actually, it's not true that we weren't expecting them. In our previous work with the Yu Deng, in our first work, we wrote down this family as a potential problem to deriving the wave kinetic equation. We didn't know what to do with it much back then. But fortunately, in this work, we realized that, and this was the starting thing that gave us hope to do the full derivation, is that we discovered an elaborate cancellation of diagrams that happens for this family, and this is why this family does not pose a lethal threat to the strategy. There's a cancellation that happens in the couples. And finally, there's a third family that I don't have time to explain to you, but it also it features a some redeeming bounds, but not a cancellation. So the cancellation is in the second family. The good news is that there's indeed only exponentially many such couples. There are only exponentially many such diagrams. Okay, so this leaves us with the second part, which is the rest of the couples. Remember, we have factorially many couples that are remaining. So the fact that those factorially many couples all feature a gain in L, a sufficiently large gain in L, is the context of our main rigidity theorem, which if I had to pick a theorem, this is the most important theorem in the work and most complicated one to prove. So what it says the following, that if you perform a type of surgery on an arbitrary couple or a Feynman diagram, and by this surgery, I mean that you remove all its regular subcouples, you remove all its irregular chains, all its type 2 chains, These are exactly the structures that I told you on the previous slide saturated the estimates. If I remove those from an arbitrary couple, then I'm left with a reduced couple of size R. And the key point of this rigidity theorem is that for this reduced couple of size R, I have a gain that is order of L to the minus CR. So the key point here is that the gain is comparable to the size of this couple. So why is this good? The reason why this is good is that the number of such couples is R factorial. The number of such couples that have a gain L to the minus CR is R factorial. And this L to the minus CR is exactly enough to offset the factorial divergence, because L to the minus CR times R factorial is less than L to the minus nu whenever R is less than a logarithm of L. Okay, and remember from previous slides, I'm only expanding up to n that is logarithmic in L. Okay, so as long as you expand up to L that is logarithm in L, you're in good shape. Okay, so this is what allows us to close the argument. Okay, so the proof of this rigidity theorem is, as I said, it's the most sophisticated part of the proof. And it involves recasting the problem of counting the couples into counting another family of combinatorial structures that we call molecules. So we have those Feynman diagrams. It turns out that they're not very convenient to do the estimates on. We recast the problem of doing the estimates on those couples into something that we call molecules. So those two things are essentially equivalent, but this is much more favorable to do estimates on it. So we reduce it to a counting problem on this molecules, and the way we do it is we run something similar to a computer program that sort of digests this molecule and breaks it down, and this would effectively allows us to count its contribution. Okay, so so finally, once this picture is made clear for the iterates, there's still the remainder term, but the estimate on the remainder term is relatively easier once you know how to estimate the iterates, and actually it can be derived from the analysis of the iterates as above. I don't have time to discuss that. So I will stop here, and thank you for your attention.
Thank you, Zaher. So we have time for questions. So please, those who have questions, turn on, as always, your camera and mic. Jan, yeah? Jan and Claude, yeah.
Yeah, thank you for the great talk. Yeah, and the great result. Yeah. So for the limit equation, the limiting equation, the kinetic equation, what do we know about the existence? What about from the PDE viewpoint?
That's a very good question, and this is what I alluded to. That so what we know about existence, we know local existence. There are some results about local existence by UNESCO, Germain, and Tran, where you assume some that the initial data belongs to some Lebesgue space, and you have a local solution. We don't have a very good understanding about the long time behaviors. The only results about long time behaviors are results of the dimension of Escobedo and Velasquez and Sofer and Tran. But again, those are our understanding here is still, I think they would agree with me that our understanding is still poor, and we need to study this equation in a more serious way.
Even in small data setting?
Even in this small data setting, yes.
That's hard, okay.
It is hard, yes. Yes, I would, well, at least it's still not properly investigated, I would say.
Okay. Mm-hmm. Thanks. Yeah.
And this is maybe one remark is that this is, for this equation, it is very important to understand what classes of initial data you are, or what classes of solutions you are studying. So the results that I mentioned are of UNESCO, Tran, and Germain. They are for initial data that belong to Lebesgue spaces or weighted Lebesgue spaces. But also of high interest are initial data that resemble those cascade spectra of turbulence. For example, initial data that look like power-like spectra or perturbation of those power-like spectra. And in that case, even much less is known. So these are all very highly interesting questions, highly interesting mathematical questions that are still not properly investigated.
For those equations, for the limiting equations, you have infinite energy, right? Or is that true? Or
well, it depends on it exactly depends on the class of initial data that you're taking. So if you take your initial data for the kinetic equation to be in L1, then this corresponds to having a finite energy for this equation. The L1 norm is the natural energy. But of course, those cascade spectra have infinite energy.
okay.
So many of the, in other words, many of the solutions that are of interest to physicists have infinite energy. And they're rather singular.
Okay, Claude, maybe you had a question, Claude? You're muted, Claude. Claude, you're muted. You have to unmute. Claude, you're muted.
Yeah, okay. I'm no more muted. Okay. Just a naive question about that. I have been exposed to several other problems where appears these trees and the pruning of the trees, which is exactly what you do at some point, which is finding which are the trees which are plays an efficient role. And they are deterministic. In the example for linear Schrodinger, nonlinear Schrodinger equation, how you get there from the linear one when you have n particles going to infinity. There is a paper of Herder, Schlein, and Yu, and you mentioned that for Boltzmann, the Lanford, if you do it the way that Bodino, Gallagher, and Ceremon did, they find out also this question of selecting what are the trees, which plays a role. Now, this exam, they are deterministic. Can you say some comment on how the randomness you put in the program, which I understand is really compulsory, plays a role in the limit?
Well, I would first argue that those problems are equally probabilistic as the setting that we are in a way, because even in the derivation of Boltzmann, you are assuming a density or distribution of the initial particles. And this distribution of initial particles is exactly the analog of the distribution of my initial data for NLS. So I'm still in a, I mean, it depends how you describe it, but I'm still keeping the equation deterministic, but I'm just taking a initial distribution of the initial data. Now, I agree with you that there's this, whenever you are doing a rigorous derivation, the key point is to the general or the big strategy is to identify the leading diagrams and then proving that everything else is subleading. So to me, this is the only, as far as I know, this is the only common things between our work and the works of the Boltzmann work, or the work of Herder, Schlein, and Yao, and the rest. There might be more similarities, but the differences between the problems becomes in terms of first identifying the leading diagrams, which might not be just the ones, as in our case, they're not just the ones that you were expecting. There are more ones that you need to find a cancellation between them. So this was also something of a novelty that I believe in this wave setting, that there is some cancellation of diagrams that need to be exploited. And then the other things which is again something that is problem dependent, which is how do you treat these factorially many remaining terms, and on what basis they are error terms. But you're right that the general strategy is fairly common when you're doing a diagrammatic approach.
Okay, thanks a lot for the talk and for the comment. Great.
Okay, Carsten, you had a question maybe?
Sorry, I wanted also to ask about the connection to the classical derivation, and so you still have this issue of the small delta. Is this comparable to what's happening at the Boltzmann situation, or do you think it's really far away?
I believe it's it is very comparable to that. I mean, the point is that we are doing a power series expansion, which just like in the case of Boltzmann, you have a Cauchy-Kovalevskaya theorem that's happening at the level of the PDE, a power series expansion that's happening at the level of a microscopic system. And for those, you are inherently led to a small delta assumption. Now, the possibility of making delta larger is the question for the future.
Do you think it would be easier here than in the classical case?
I don't know. I cannot tell, to be honest.
Thank you.
I still don't see a redeeming feature here compared to the classical cases. They're probably, but this is a guess. This is just a guess. Probably equally difficult. Not sure.
Chiara, you had a question? Yeah.
Yes. Thank you very much for the very nice talk. It was also very clear. I have some questions, and one was already asked right now. So I guess, as far as I understand your result, I guess the delta really plays the role of the small time of Lanford result. So you are on the right time scale, but you have this delta in front. And the question is, where does it come in the proof, the delta?
Excellent. So this is exactly what it comes in what I mentioned about the iterates, that the n plus first iterate in this setting is only better than the previous iterate by a factor of delta. By a factor of delta. And as a result, the estimate that I have for the nth iterate is only delta to the n. Okay? So the estimate, or in other words, sum of the couples, so this nth iterate of the NLS equation, this is over here is a sum over couples, sum over diagrams, or if you like, or we call the diagrams couples. Okay, so this is a sum over couples. And some of those couples have size order of delta to the n. These are the largest couples have size delta to the n. So it's here where it appears. And so what you really want is that at some point you want to stop the iteration and say that everything else in my expansion, you want to stop the expansion and you say everything else is a remainder. But for you to do that, you want this delta to the n to be less than L to the minus nu, be a negative power of L. And as a result, this is what chooses n for you, chooses n to be logarithmic. And of course, for this, you need delta to be less than 1.
Okay, thank you very much. Then if I may, I would have other 2 questions. So maybe I can ask one, and then you stop me if it's too much. Okay, Clément?
Yeah, go ahead. I think we are using the break. I will push the next talk by a little bit. Go ahead.
Okay, thank you. So the next question is more on a general, to understanding a bit what's the state of the art. So you mentioned that there are results also in the inhomogeneous case. And then I'm not sure whether this is again reaching the right time scale, or it's more in the direction of your previous work with.
It's more in the direction of the previous work. So in the inhomogeneous setting, we still cannot reach the kinetic time scale. This is something, this is a work in progress that I'm doing with my postdoc and Jalal Shatta and Yu Deng. We're trying to do the derivation in the inhomogeneous setting.
And for that, do you, I mean, if you want to keep it secret, I understand, but do you, can you give us an idea on the initial data? How does it look like in this case when you want to?
Yeah, okay, absolutely. Yeah, no, absolutely, yeah. I mean, there's some level of, in that setting, there's some level of freedom, how you choose initial data and how you set it. So in that case, we set the problem on RD. Okay, so the setting we consider NLS, for example, on RD. And so if you think about our current setting, what we're doing is that we're taking periodic data on RD. So this is homogeneous case, if you like. what we're doing is that we're summing k in ZD sub L here, A sub k, okay, A sub k, e to the I, so this is, let's talk about the initial data, e to the I k dot x. And this A sub k, we are sort of random, so this is, okay, so this is randomizing it by maybe by some eta sub k. Okay, and A sub k was square root of an initial, which is the initial data for the kinetic equation. So in the inhomogeneous setting, what we do is that we take the initial of x, we introduce another scale, we allow now ak to depend on x, okay? So, but through another scale epsilon, say, so we have k zd sub L, ak of epsilon x. So rather than being a constant, this ak, now it has an inhomogeneity at scale. So this epsilon is sometimes called the scale of the inhomogeneity. And then you can, okay. So this is what introduces the inhomogeneity, and this was what introduces a transport term in your equation.
So the epsilon is not related to the other parameters.
So yes, I mean, now then you would have, so in the inhomogeneous setting, you have three parameters. You have the alpha, which is the strength of the nonlinearity, L, which is, so L here, it's, you can keep on calling it the size of the box, but really L is the number of waves, or L to the D is the number of waves. Okay, and then you have epsilon, which is the scale of the inhomogeneity. And of course, the notion of scaling low in that setting gets a little bit more involved, because now you have three parameters. I could also tell you that, so this scale, the scale of homogeneity tells you also that, gives you the scale of the transport. So if you do a formal derivation for the corresponding interesting quantity, you would get, or which is n, you would get dtn plus something like epsilon, epsilon c dot grad x of n equals to the kinetic equation, which is alpha squared times the collision curve. Okay, plus lower order. So this is formally. Now, if you want to see the inhomogeneous equation, you want to equate this to this. So then you want, because you want the strength of the transport to be equal to the, this is sometimes called the mean free path. And this is the, you want that at the time it takes a wave packet to move a distance, L is equal to the mean free path. So you take epsilon equals to alpha squared, something like that.
That's clear.
Okay, so there are some conditions. It gets a little bit more involved, but we're hoping that at least we'll use a lot of the analysis that we did in the inhomogeneous setting. I should point out that there is still a lot of new elements coming in this inhomogeneous setting that we're still working on.
Thank you very much.
Okay. Yeah, so you had okay, maybe I suggest otherwise there will be zero break. Maybe let's keep the next questions. You can stay in the room and continue actually.
Yes, I'll stay in the room.
So those interested in, I had questions as well, but let's do the break. Those interested in interrogating Zaher more, stay in the room, but let's take 20 minutes break. And Martin, you're okay to start at 4:10 instead of 4, is that okay?
Yep, perfect. Yeah.
So that people can, I don't know, grab some tea or whatever. So let's have 20 minutes breaks, and those who want to continue to bombard Zaher can stay in the room. So Chiara, go ahead. You had another question.
So Zaher, if you wanna take a break before.
No, absolutely. It's.
And I have only another one, meaningful at least, I think. So you mentioned that your ternary trees and the molecules you constructed, they are essentially equivalent. What do you mean by essentially?
They are equivalent. I mean, there's
They are
the problem is that let me tell you why you need this molecule formulation, which is or why we introduce this molecule formulation. The reason for that is that if you look at this couple over here, this is a Feynman diagram, but you notice that this leaf is paired with this leaf, right? So what's happening is that at the level of Feynman diagrams, this pairing structure is a very non-local structure. You can have a leaf that is paired with another leaf very far away in the diagram. Mm-hmm. And this is not good when you want to do counting problems on this diagram, because once you account for this leaf, for example, or the decoration of this leaf, you have effectively accounted for the decoration of its paired leaf, because they have to be decorated by the same thing. They are paired to each other. So the reason we introduce the molecules is that the molecule makes this pairing structure a local structure. Mm-hmm. And the idea here is somewhat natural. Retrospectively, it's natural, if you like. So what you do is that each atom in this molecule, so the molecule is formed of atoms and bonds between the atoms. Each atom in this molecule corresponds to a we call this a nuclear family, to one nuclear family. So this is a nuclear family, this is a nuclear family, this is a nuclear family, and this is a nuclear family. Each one of those corresponds to an atom. And a bond between those atoms corresponds to some pairing, for example, between the leaves in those two nuclear families. So as such, they are, you can actually, they're almost equivalent if you put enough information. They are equivalent if you put enough information over here, but some of the information you really do not need. So that's why I said they're almost equivalent. But we are starting to realize that could be very important. It could be a very important perspective to do further results in this direction. But the key point is that you really need to make this pairing structure a local structure rather than a non-local structure. And this is what's done by the molecules. Somehow they're natural. Somehow they're natural, and they turn out to be very cool objects.
So for this, then you really use the fact that you are looking at the modes in a sense. So it's
yeah, absolutely. Because the problem really is that you have this diagram, but you want to count the number of decorations of this diagram. A decoration of this diagram is, as I said, is an assignment of a wave number to each of the nodes of this diagram. So the problem can be boiled down to counting the number of decorations that you can assign for such a molecule. So it's a counting problem. It's a combinatorial problem in the end. And the point is that it's much more effective to do this combinatorial problem at the level of the molecule rather than at the level of the Feynman diagram.
Understand. So in a sense, this would be difficult to translate it in the classical setting of Boltzmann, where you also have trees with a different meaning.
Yeah, I don't know about that. That's a very good question, actually. I would assume that this is sort of fairly general because
if I understand correctly, for your like from the first, let's take for example your tree on the left hand side of the screen. Yeah. Then you have K and then you have L, E, M, and these L, E, M are chosen in a way that like L minus E plus M has to be
exactly
equal to. Mm-hmm. So it's
yes.
Is it somewhat related to the fact that you want some momentum to be conserved, or?
I mean, this is just K plus E is equal to L plus M. This is, and you also have actually a condition, something that says that K squared minus L squared plus E squared minus M squared belongs to some interval. Mm-hmm. So this is
in some way it's a collision, isn't it?
It is a collision, yeah. I mean, it is a collision. It's sort of, it's funny that this analogy with Boltzmann can be pushed quite a bit. It's funny that it can be pushed quite a bit, yeah. So this is just telling you that you are, in some sense, counting the number of collisions, if you want. Yeah, I wouldn't actually. That's a good question. It's whether this approach or this perspective could be translated to Boltzmann. That would be a very interesting. I wouldn't be surprised actually if it did, because it's a fairly robust thing. It's more of an idea rather than just a technical thing. It's the idea is that you want to make this pairing between diagrams a local thing. You want to make it a local problem rather than a non-local problem. Because as you see here, those leaves can be paired to each other, and they could be very far away in the diagram. And if they're very far away from the diagram, you cannot count, you cannot do the estimates in an effective way. Whereas here, this pairing between them corresponds to a bond between two molecules. Between two atoms in the molecule. So this makes it into a local problem. And once you account for this, you remove this molecule, you break up this molecule, and your strategy is to, in a way, digest this molecule, to break up all the bonds, and you're to be left with things that you can easily count.
If I can add a question to your questions, Chiara, on these parallels. Do you have a similar, or do you have a counterpart of the notion of mean free path? And how does it compare to L? So like the average distance between two interactions of your waves, and how does it compare to the size of your box?
Yeah, so I don't see that that analog, but when I talk to Herbert Spohn, for example, he uses that notation a lot. So I came to call also the mean free path this kinetic time. Herbert calls 1 over alpha squared the mean free path. Okay, and the comparison of this mean free path to L is exactly your scaling law.
That would be equivalent from what we know, say, on more in our community, what we call weak coupling, I would say, if you pair it like that.
Yeah, that's where I was going to, Chiara, exactly. So it means, so hang on, Zaher. So it's 1 over alpha square, right?
Yeah.
And that's the mean free time, sorry. What is the mean free distance?
Oh, that's, I think, time, maybe. I don't know what the mean free distance would be, to be honest. I mean, there's probably limits to how much you can push the analogy, right? I mean, you have waves that are...
I'm not sure, because you end up with an equation that is nonlinear, but nevertheless has a structure of sort of jumps, and jumps are localized. So
what do you mean by jumps?
Even if your theorem for the moment you reach the critical time not with X, of course, I guess at some point you or different groups.
So I can maybe make more sense of your questions in the inhomogeneous setting.
Yeah, exactly. You need probably X to make full sense of it.
Yeah.
But then,
so in that case, maybe it's 1 over epsilon. This is the equal. This is what I wrote over here. That you have this is the mean free time equals to what I call the transport time. That this is, in other words, you can interpret this is that you can interpret this epsilon, or 1 over epsilon is the time it takes a wave packet to traverse distance L, and you want to equate that to this. So I think that might be exactly what you're saying, that equating you want to equate the alpha squared over here, which is very much related to the kinetic time, because the kinetic time is exactly 1 over alpha squared. And you want to equate it to the transport time scale, which is 1 over epsilon.
But hang on, in your scaling, so alpha and L were related, no, in the scaling of your main theorem.
Yes, but this epsilon is a bit different than L. L in this setting, L in the homogeneous setting is the number of waves. Now in the inhomogeneous setting, you still have a number of waves, but you have an extra parameter for the scale of the inhomogeneity.
Ah, okay.
Okay, so this equality between epsilon and alpha square is an equality that you need between the scale of the inhomogeneity and the mean free time, if you like.
Okay. Okay, so it's conceivable that in the inhomogeneous case, you could have a fixed box and the kinetic limit at the right scale.
Fixed box.
If you want,
you can formulate those problems in very, very different ways, and they're yes.
I know there are many parameters. So maybe let me tell you what I have in mind physically, and then we can, because there are too many parameters to play with.
Yeah.
What I'd like to know is whether your waves have time to fold on the period many times between two interactions.
Absolutely, yes. So this is our setting, yes.
Because the Lanford theorem doesn't use that. It's an ergodization property when you fold on the torus many times. That is helping the decorrelation. You see what I mean?
I don't think it is helping, but let me. So this is what is. I understand what you mean. So even in the homogeneous setting, although it is more appropriate, more adequate in the inhomogeneous, but even in the homogeneous setting, you can think of you're working on a torus of size L, and you're thinking, oh, I'm thinking about wave packets of frequency order of 1, then those wave packets will take time L in order to wrap around the torus. Right? And then, so whether the question is whether your mean free time is bigger than L or smaller than L. Okay, so now those, again, these were sort of many, there were discussions that I had and was quite illuminated by discussions with Herbert, is that in the homogeneous setting, this really does not matter, because in the homogeneous setting, you're putting yourself in a situation where the field is the same everywhere. Mm-hmm. Okay, so whether you wrap around the torus once or twice or 100 times, okay, the field is exactly the same. The field is homogeneous. So those considerations become important when you're in the inhomogeneous setting.
I get it. So we'll have the answer when the critical case will be reached for the inhomogeneous theorem.
So in the inhomogeneous theorem, the difference is that in the inhomogeneous theorem, if you like, there is a preferred scaling law, which is this L, scaling law when the kinetic time is equal to L. This is the time for the wave packet to wrap around the torus. In the inhomogeneous setting, there is a preferred scaling law. But in the homogeneous setting, there is no preferred scaling law.
I see.
Actually, you can formally start with the inhomogeneous equation with this preferred scaling law and derive as a limit the homogeneous equation formally again for all the scaling. So all the scaling laws of the homogeneous equation appear as limits, as homogeneous limits of the inhomogeneous equation. This is a delicate issue. We wrote a small note about it, but we didn't publish it yet. But these are very good questions, very good questions.
Okay, I think we have to stop, at least for now, to interrogate you. Maybe I'll just grab a glass of water, but maybe you could remove your screen sharing and Martin, yes, if you can screen share